Okay, welcome everyone to our Space West seminar webinar series. And so today will in fact be the last webinar of the series for 2021. And our speaker is Mathews Jacob. So let me give a brief introduction or a biography of Mathews. He received his BTech degree in Electronics and Communication Engineering from National Institute of Technology in Calicut, Kerala, in India, and the ME in Signal Processing from the Indian Institute of Science, Bangalore. And then he received the PhD degree from the Biomedical Engineering Group at the Swiss Federal Institute of Technology in 2003. And then he was a Beckman postdoctoral fellow at UIUC in Urbana-Champaign. He is now a professor in the Department of Electrical and Computer Engineering and heads the Computational Biomedical Imaging Group at the University of Iowa. And his research interests include image reconstruction, image analysis, and quantification in the context of magnetic resonance imaging. He has received many awards, including a Career Award from the National Science Foundation, the Research Scholar Award from the American Cancer Society, and the Faculty Excellence Award for Research from the University of Iowa in 2021. He's associate editor for IEEE TMI and has served as associate editor for IEEE PCI. And he was a senior author on 2 Best Paper Awards and 1 Best Machine Learning Paper Award from the IEEE ISB conference. And he was also the general chair of the IEEE ISB conference in 2020. So for this talk, he's going to be speaking on model-based deep learning for large-scale inverse problems. So without further ado, let me hand over the speaking over to Mathews.
Okay, thank you, Sai, for that kind of introduction. So thanks again for running this series. I mean, this has been really very helpful. So today I'm going to talk more about model-based deep learning for large-scale inverse problems. So I know a lot of you are working on model-based deep learning, and when you look around, there's a lot of work on smaller scale inverse problems. So basically, when we are trying to reconstruct a single slice or a couple of slices. So our focus is to, or the focus of this talk is to take many of these ideas that have been well developed to large scale inverse problems. So I'm going to focus mostly on MRI in this talk, but as most of you are aware, the computational imaging community is aware, these methods are widely applicable to other areas as well. So our group had been mainly working on MRI. There are 2 main thrusts. So the first one is high resolution brain scans for Alzheimer's disease. So basically, if you're putting somebody on the scanner, like in 1 minute, you can get images that look roughly like this. Okay, so so you get about 1 millimeter isotropic resolution. And if you do a segmentation of the hippocampus, you will see something like this. Now, if you have the luxury of scanning the same person for 8 hours, you can get a much finer spatial resolution and a lot of details. And the hippocampus, the same hippocampus, can be seen in a lot of detail. Now, if you do the segmentation there, you would see a lot more details. And the benefit for doing something like this is that you can diagnose or you can detect Alzheimer's progression much before the clinical indications appear. So, but unfortunately, we cannot scan a subject for 8 hours. So the question is, can we get something like this kind of resolution in about 10 minutes? And that's one of the focus areas in our group. Another focus area is free breathing cardiopulmonary imaging. So I've been working with a group of doctors who are interested in pulmonary hypertension. So this is somewhat like the normal hypertension, except that this is elevated blood pressure within the lung. And unfortunately, unlike the regular hypertension, this cannot be detected using a cuff monitor or something like that. So it's a really invasive procedure to measure the elevated blood pressure in the lung. And as a result, it's underdiagnosed. So usually this is detected very late in the disease when the right ventricle has enlarged and it's too late to intervene and make any difference. So in all these cases, I mean, we need to collect high resolution data and, you need to image fast and so on. But, as many of you know, it's hard to do that with MRI because it's a slow imaging modality. So we need to collect all this case-based data. So the data is acquired in the Fourier domain. So collecting the data is expensive in terms of time. And as a result, we often have a three-way trade-off between the available scan time, the achievable spatial resolution, and how many slices or how much volume you can cover. Now, compressed sensing made a huge impact in this area. So, basically the idea is to undersample the Fourier grid and then try to reconstruct this using a convex optimization scheme, using some kind of a sparsity model on the images. So this became FDA approved a couple of years back, and it's now widely used in the clinic. More importantly, compressed sensing created a revolution where the idea of sparsity was generalized in multiple different ways. I mean, for example, people have looked at, the basic assumption here is that the data, so by data, what I mean is, you can extract patches from the images, you can take whole images from a time series, or you can look at the pixel profiles and think of all of these as signals. Now, if you look at signals from a data set, you can think of it as lying on a smooth surface in a high dimensional space. So basically, there's a lot of structure in the data, and a lot of models had been used to capture the structure. And these are usually called as shallow learning method models now, because, just to contrast it from deep learning. So some of these methods, I'm not going to talk a lot about all these methods. I mean, you can use a low rank penalty. You can use a dictionary penalty, which uses a union of subspaces approach, or a nonlinear approach such as smooth manifold model. So these are the traditional approaches that kind of came after compressed sensing, and they are widely shown to be very powerful in a variety of MRI applications. Now, we all know that deep learning had made a huge impact in this field as well, starting from around 2015. So we know that deep learning methods can represent images in a far more efficient fashion compared to some of these classical methods. Now, why do these models outperform classical methods? So that's a relatively open question. So a lot of smart people are already working on this area. I mean, even though it's not fully understood, there are some interesting works from Zhang Chul's group. And this is a recent paper that came from Georgia Tech, which basically looks at representing images on low dimensional manifolds using deep ReLU networks. We also did some work along these lines. I'm not going to go into details, but I just want to give you a gist of what the message is. So let's say all these signals are lying on a smooth low dimensional surface in higher dimensional space. Now, if they can be represented, so these surfaces, if they can be represented as the zero level set of a band limited function, so if they lie on the zero set of a smooth function, which has a band limited representation like this, then we can come up with an exponential mapping and represent them more efficiently by using a neural network. I mean, so this can be a one-layer network or a deep network. So the main message is that if the signals and functions lie on smooth surfaces, which are zero sets of some functions, then you can represent them and learn them efficiently using few samples. So I won't go into the details of this work, but I just want to mention that the theory on all these neural network methods are still emerging, and I think it's a really exciting field to be in. So motivated by all this excellent performance of neural networks, a lot of people around 2016 had been working on applying this in inverse problems. For example, like work from Zhang Chul's group and also from Michael Unser's group looked at taking a standard network like a UNet or a residual network and feeding it some aliased images or undersampled images and train it to do the reconstruction. So this is a completely data-driven approach, I mean, which basically does not use the physics of the approach. So that's also a limitation. I mean, because you have to learn the physics and the image structure, it often requires a lot of training data. And another problem is that it has low interpretability because you're just training a neural network. I mean, it's very hard to understand what it's actually doing. And again, it might be difficult to adapt it to new acquisition settings. So this is going to be the overview of my talk. So I'm going to talk a little bit about model-based deep learning, basically a review of what has been done here, and also talk a little bit about deep equilibrium models that are emerging as powerful alternatives for these unrolling-based approaches. And then I'll talk a little bit about monotone operator learning and unsupervised learning and so on. So how does these methods work? So basically, you pose it very similar to a compressed sensing setting. So you have a data consistency term, which looks at how much different is the measured data from the measurements on the reconstructed image. And the second term is a regularization term. And so this is usually implemented using a neural network. So let's say you have a neural network, which is a predictor of noise and alias patterns in X. So if you think of this optimization problem, the goal here is to determine an X that is data consistent. So this term ensures that it's data consistent. And this term will give you a high cost if there's aliasing in the data. So you're basically trying to find an X that is data consistent and also minimize aliasing. So this whole area started with IstaNet, which was introduced by Gregor and Lachlan in 2010. I'm just showing a few examples here, and most of our discussion here will be based on this model-based deep learning work. But this area is very rich, and a lot of papers are still coming out in this area, which is really emerging to be a very powerful alternative to standard deep learning methods. Now, this NW of X, it's usually implemented as a residual network. And when it's implemented as a residual network, you can think about an iterative algorithm such as this to implement or to solve this. Now, if you want to just do forward propagation, if you just take a trained network, if you want to do a forward propagation, it's very easy. Okay, so you just need 2 layers, and you just keep on iterating this until for a certain number of iterations. But when you want to train this, you can unroll this to a certain number of steps. For example, 10 in our implementation. So you unroll this to 10 steps. So you have the same denoiser. So as a result, we will have the shared weights. I mean, so these weights are shared. And this network, you can think of it as a single neural network and can be trained end to end. So the benefit is that it is using the learnable blocks, which is training the image, learning the image content. And you have the data consistency blocks, which are enforcing the consistency with the measured data, or in other words, it's using the physics of the acquisition. Now, how does this compare with plug and play methods? So there's excellent work by Charlie Bowman's group and a lot of other groups on plug and play methods, which uses a pre-trained denoiser, which was trained to denoise Gaussian noise. And then once it's trained, you can use that in an unrolled approach or an iterative approach. So if you compare this with this end-to-end training, we see that end-to-end training gives a significant boost in performance because you're not training an arbitrary neural network, which is a denoiser. You're training a neural network that is customized to the specific imaging physics. And another big benefit is that we are using relatively smaller neural networks and iterating them. So the number of parameters that you're trying to learn is much smaller. As a result, you need very few training samples to get good performance from these methods. Okay, we have applied this to a variety of applications. I'll just go through them briefly. So this is one example done by Florian Noll. So it's in the review paper. So they basically compared a model, which is the proposed algorithm, and with parallel MRI, compressed sensing, and also variational network, which is one of the earlier methods. And with this approach, we could get pretty good performance, and pretty good comparison with the reference data. Again, this approach can be generalized. So in the previous work, we assumed that the coil sensitivities were known. You can also extend to the case where the coil sensitivities are unknown. And this is a model setting which uses known coil sensitivities, and this is the approach which does not use coil sensitivity. So you get somewhat qualitatively equivalent results, or maybe a slightly better PSNR by using this uncalibrated approach. You can also combine this with segmentation. So you basically, it's a multitask learning framework. So instead of only using the reconstruction task, you can add a segmentation task. And that allows the network to generalize better, and you get improved performance. So this is the case without the reconstruction, the segmentation task, and this is the one with the segmentation task, and you get some improved performance. You can apply it to other settings. For example, this is reconstruction of multi-shell diffusion data. So this is a long scan. So because you need to collect multiple images per slice. So the data is usually collected on a diffusion shell. So you need to sample a lot of points on this diffusion cell, each of which will be an image. So the acquisition time is really long. So, but you can combine all of this and do a joint reconstruction by using this model-based deep learning fashion. And of course, you can apply it to dynamic MRI, which I'll talk about shortly. Now, these methods are really powerful and shown to be very useful in a variety of settings. But what are the challenges here? So the first of all, all of these methods can be trained for single slice, but when you extend it to multiple slices, it often does not fit on the GPU. Okay, so the maximum number of unrolls we can fit on a regular GPU is about 10. So this means that we cannot extend this to multiple slices. Another big problem with neural network approaches that are emerging is the potential sensitivity to input perturbations. Okay, you can train a model to do a pretty good job in reconstructing, but what if you add an adversarial perturbation to the input? I mean, what happens to the output? I mean, are you going to suddenly get crazy results? Now, thanks to a lot of groups like FastMRI and so on that have provided a lot of fully sampled training data in the small scale setting. Unfortunately, this is not available in the large scale setting when you're trying to reconstruct images at very high spatial resolution. Of course, in many cases, it's not possible even to collect that data. Now, we want to extend this to dynamic data, which is what our clinical collaborators are pushing us to. So how do we extend it to the reconstruction of multiple 3D volumes over time? So these are all challenges that motivated us to come up with this research. So I'll do a quick review of deep equilibrium models, which is one way to get out of this trouble. So this all started. Yeah, sorry. Yeah, go ahead.
There is one question in the chat. Would you like to answer now or at a later point?
Okay, what's the connection of this stuff with your announced idea that the data observed can be treated as a low-dimensional cross-sections of more dimensional data? Yeah, so basically, this network, so let me just go back. So we are learning a network here, and this network is a good denoiser, or you can think of it as a projection onto a manifold, not for any arbitrary image, but only images in the manifold that we are training it with. Okay, so essentially, it works as a good denoiser for the class of images you're interested in, and not for any arbitrary images. So that's the connection with the manifold methods. So did I answer your question, or you have further clarification? You need further clarification. All right. Thank you. All right. So let me just talk about deep equilibrium models that started with this work. So this was a work basically which shows that you just need one physical layer and you can do the forward propagation and backward propagation by using an iterative algorithm. So this work was generalized to the imaging setting by these excellent papers. I mean, for example, I think Rebecca Willett gave a talk a couple of times back, which talked about the application of deep equilibrium models to imaging applications. So let's look at how these methods work. So before we go on to deep equilibrium models, let me quickly review the standard backpropagation. So let's say you have a Hermitian B that is going into a UNet or something, and out comes X, which is compared to the ground truth images. And let's say this is a supervised training loss. Now, to train this, we need to compute the gradient of the loss, which is given by this equation here. Now, if you have a single layer model, it's very easy. So you compute the gradient of, so the Jacobian of this mapping, and multiply it by the gradient of this loss with respect to X, and we are done. However, when you have an iterative algorithm, you might have an iterative rule. So xk plus 1 is f of xk and theta, which is the parameter of the network. So you feed in xk, and what comes out is xk plus 1. You keep on iterating this until convergence. Now, so under proper conditions, this algorithm will converge to a fixed point. And now you can compute the Jacobian similar to the previous setting by using chain rule. Now, with some mathematical manipulations, you can show that the loss, the derivative of the loss with respect to theta can be written as shown here. So if you compare it with the previous setting, you see that the additional term is this term here, this I minus the partial derivative of f with respect to x star inverse. Now, the good thing is that this term, this S term, can be computed by using a iterative algorithm. So you basically think about an iterative algorithm, and you can iterate that to do the back propagation. So the essence of the story is that you just need one physical layer, and you can do forward propagation and backward propagation by using an iterative rule. So this significantly reduces the memory demand. Now we don't need to unroll the algorithm to do training. We just need one physical layer, and you can compute the forward propagation and backward propagation using this approach. Now, let's focus on one of these algorithms. So let's say the proximal gradient algorithm. Yep. Go ahead.
Yeah, maybe just a discussion point. I think maybe a limitation here is that if the fixed point in that equation x star equals f of x star, if those fixed points are not unique, but rather a set, then that may create potential issues, because then we would need to specify with respect to which x star the gradient is being back propagated, or it may, if not, I think there may be potential numerical issues.
Excellent point. Yeah, that's an excellent point. So thanks for raising that. I think I'll talk about that in a short while. So that's one of the limitations of DEQ models, and I'll talk about that shortly. Okay, so basically, all of this assumes all of these methods work really well if it converges to a unique fixed point, as I just pointed out. So let's focus on one approach, which is a proximal gradient algorithm. So you basically do one step along the cost function, and then you apply a proximal mapping. And usually this proximal mapping is replaced by a learned neural network. Now, there are some excellent convergence guarantees from Professor Wotao-Yin's group. So they showed that this proximal gradient algorithm, as well as the ADMM algorithm, converges under some conditions. So let's look at these conditions a little closer. So if you look here, you see that the convergence depend on mu, which is the minimum eigenvalue of a Hermitian A. Now, this is guaranteed when A is a full rank matrix, but unfortunately it does not hold for CS problems. But I must tell you, this is just a sufficient condition and not a necessary one. So the algorithm might converge, but the guarantees might not work. Okay, so I mean, in practice, these algorithms are shown to be working well, but these guarantees do not hold in the compressed sensing setting. Now, another challenge is that one of the requirements is that this proximal mapping, which is implemented by using a neural network, you need to impose a Lipschitz constraint on the neural network. And this is usually introduced by using spectral normalization. So essentially what you do is you have a long network, you just take every layer and constrain its spectral norm to be 1. And this is an upper bound for the Lipschitz constraint, and that's how it is imposed. So this, in our experience, restricts the representation ability. So that's another challenge with this DEQ models. Sorry. Now, just to answer Sai's point, so the question is a fixed point unique? I mean, it's shown that it'll converge to a fixed point, but maybe the fixed point is not unique. Now, is the fixed point stable to input perturbation? What if you just make a small perturbation to, oh, sorry. So is a question, is the fixed point stable to input perturbation? Now, again, can we realize an algorithm with guaranteed convergence in the CS settings, and can we reduce the performance loss from spectral normalization? So these are the points that I would like to address in this monotone operator learning framework that we are working on. So again, this is motivated by some excellent work from Winster and Coulter, and also from Jean-Christophe Pesquet. So what exactly is a monotone operator? So I can loosely, this is a generalization of a positive definite linear operator. So the definition is as shown here. So f of x minus f of y. So x and y are two images, and f of x and f of y are the outputs. So you look at the difference between the outputs and take the inner product with x minus y, and this should be greater than the difference, the norm of the difference between them. And if it's a linear operator, f of x minus f of y is basically f of x minus y, and you can see that this is the definition for a positive definite operator. So this just generalizes the positive definite operators to the nonlinear settings. Why is this important? So when you have a convex functional, for example, psi of x, its partial derivatives or its gradient is shown to be a monotone operator. Now, if we have a regularized image recovery by using a convex cost function, as shown here, the stationarity conditions will give you g of x plus f of x is equal to 0. So g of x is the gradient of the data consistency term, and f of x is the gradient of this penalty term. So now our approach is to learn the monotone operators directly. And this is one small difference with these methods is that these methods do not directly learn f, but they learn resolvent operators of f. Okay, so it's a minor detail, but I just want to mention that connection. So this allows us to come up with an alternate proximal gradients algorithm. So basically, we need g of x plus g plus f is equal to 0. So you can rewrite the same thing as I plus alpha g minus I plus alpha f x is equal to 0. So you can see that this I and I will cancel. And if alpha is greater than 0, you basically get the same equation. And now you can rewrite this as x star is equal to I plus alpha g inverse I minus alpha f x star. And if you just substitute for g and f, you get this equation here. So this is slightly different from the traditional proxgrad method. So the traditional proxgrad looks at a gradient of the data consistency term and then projects it to the space of, basically that's a proximal gradient on that. Now this approach is similar. It does a gradient along the penalty term followed by a projection on the data consistency term. So both of them are forward-backward splitting. The only difference is that you're swapping f and g in these two cases. So why do this? So the traditional approach uses this, and for convergence, we need a Hermitian A to be positive definite. Okay, and unfortunately, in compressed sensing applications, it's not valid. Now, in the new approach, you are swapping f and g. Now we just need this term to be a monotone operator, which is a generalization of positive definitive property. And as a result, it will be valid for compressed sensing problems. So we can come up with a theoretical bound, a guarantee, which says that this algorithm will converge when this condition is satisfied, where L is the Lipschitz constant of f. So now there is an important question, okay? So all of this is guaranteed if f is monotone, okay? How do you guarantee that it's a monotone operator? So in this paper, they looked at one approach for guaranteeing the operator to be monotone, but it's only valid for single layer networks, okay? It's not general enough to be applicable to ResNets and UNets and so on. So how can we come up with an approach where we can constrain a neural network to be a monotone operator? So our approach is really simple. So we just constrain it to be a residual operator with a Lipschitz constant of epsilon. So you write f as I minus h, where h is a has a Lipschitz constraint as shown here. So if h is a Lipschitz constraint network, we can, the consequence is that f is monotone with 1 minus epsilon, and it's Lipschitz with 1 plus epsilon. So this immediately gives you this guarantee. It says that the algorithm will converge if alpha is less than this term here. And the benefit here is that if you come up with any Lipschitz constraint network, you can use it. It can be a UNet, it can be a ResNet, whatever you like. Now, I just want to make a connection with model. So this algorithm is basically a damped version of model, okay? Especially if you set alpha to be equal to 1, this term disappears, and what we get is this equation here. So this is basically the iterative algorithm we used in model. So we are adding an additional damping on model. How does this help? So the model, for convergence, we require the Lipschitz constraint of h to be less than 0.24, okay? Again, the Lipschitz constraint can be thought of as the representation power of a network. A network with a higher Lipschitz constant will have higher general representation power, whereas a network with a lower Lipschitz constant will have lower representation power. So if we need to iterate model for convergence and for this guarantee to work, we need the Lipschitz constraint to be less than 0.24, which is really bad. On the other hand, if we add this damping, we can increase the Lipschitz constant closer to 1, which is closer to what the traditional DEQ approaches can guarantee. Now, the nice thing with this monotone framework is that we can guarantee uniqueness. So the fixed point is unique if the Lipschitz constant is less than 1. And the nice thing is that this is irrespective of the choice of the A. So basically, there are some methods that are out there that just recently came out. So they look at some conditions on A, such as the set restricted eigen property. Using that, they have shown that you can guarantee uniqueness, but those conditions are a little hard to verify. Whereas in this case, you don't need any conditions on A. It is guaranteed to have a fixed unique fixed point. Now, you also have these robustness guarantees. It basically says that if you create a monotone operator, or if H is Lipschitz constraint, you get a bound on the Lipschitz constant of the fixed point. So this is really nice, which basically shows how much robust the output is when the input gets perturbed by some noise. Now, this is a little hard to understand, so because it's a very complex expression. So we can just look at a limiting case when alpha goes to 0. So that's when the Lipschitz constant of the network comes closer to 1. Then you get this simple relationship. The Lipschitz constant is less than lambda divided by 1 minus epsilon. So this shows that as epsilon, which is a Lipschitz constant, when it approaches 1, it becomes highly unstable, or it becomes very sensitive to adversarial perturbations. But by controlling the Lipschitz constant of the network, you can bound the adversarial robustness. So you see that there is, as people have hypothesized, there is a trade-off between the representation power or the performance of a neural network and the adversarial robustness. So when you get higher performance, the price to pay is the robustness to adversarial perturbations, at least with this framework. Now,
Mathews?
all of this, yeah. Go ahead.
I was wondering, so is there well, I mean, it's good to have a unique fixed point, but is there sort of a con to that, in the sense that going back to things we know from optimization, compressed sensing was all about solving the convex L1 norm optimization, but then later on you worked on other problems where the problem is fundamentally non-convex.
Right.
But there may be better representation potential in models that lead to non-convex optimization compared to traditional L1 compressed sensing. So what is your thought in terms of would that translate to having to our understanding that maybe having non-unique fixed points is probably a good thing in terms of giving a richer representation, but then you lose something in terms of using some of these techniques?
Yeah, I totally agree. I mean, again, our focus here is to come up with something that's safe to use. I mean, if you have a robustness property, I mean, we know that the perturbation cannot exceed something. So that's a nice property to have. But of course, you need to have, you're probably paying a price in terms of representation ability. I mean, I'll show that shortly in our results. We get better performance by using something like model, which does not have this guarantee. I mean, but I don't have those results here, but some of these models are a little bit sensitive to adversarial perturbation. So it's a kind of a trade-off, whether do you want to have a safe model which will not blow up, versus do you want the best possible performance? So I totally agree with you. I mean, maybe it might be possible to go out of this framework and come up with a model that is simultaneously safe and also robust. But that's, I believe, an interesting idea to pursue.
Great, thanks, Mathews.
I take your point. Yeah. All right. So now the question is, how do you enforce this Lipschitz constraint? So one possibility, as I mentioned earlier, is spectral normalization. So we can take, you can consider a deep network, and you can constrain the spectral norm of each layer to be less than equal to 1. And you can use that. Okay, that's a really simple approach. Unfortunately, this is just an upper bound for the Lipschitz constant. And as a result, if you use networks like that, at least in our experience, this significantly restricts the representation power. I mean, there are hacks to going around that. I mean, by using either batch normalization and together with some clipping and so on. But we just removed all of that. And if you just use spectral normalization, we were getting lower performance. Now, what we did was just to use an adversarial Lipschitz regularized training. So we have the standard supervised loss, and we computed the Lipschitz constant by using a gradient descent. Okay, so this is somewhat similar to GANs, where you have this min-max optimization problem. So we are trying to minimize the supervised loss, but then we are also going to look for the maximum of this term. So you're basically looking at H, which is a residual network, and you're adding a little bit of noise to it, and you're looking for what is the worst noise that will perturb the output. So when we do this joint optimization, we are enforcing the Lipschitz constraint without requiring the spectral normalization. And another benefit is that this can be used for any network, I mean, UNet or ResNet, whatever you like, unlike the spectral normalization approach, which just requires a single linear network, a cascaded network. So how does this work? I mean, this is just a basic validation. So we just took a small data set, which has about 10 subjects, and trained this using multiple networks. So the red one here is the Lipschitz, the spectral normalization network. And so each layer is constrained to have a spectral norm of 1. And you can see that as the training proceeds, the Lipschitz constant, so the Lipschitz constant was evaluated using an adversarial approach. So we see that it goes up and stabilizes to something like 0.7. Now, if you use the unrolled model, so the green one is a model with 2 iterations. So you see that the unrolled model has a Lipschitz constant of something like 1.1 or something like that. This is for each layer. So together for 2 layers, it's 1.1 to the power 2, roughly. And if you use a 10-layer model, this unrolled network, you get a Lipschitz constant which is slightly higher than 1. Now, if you use the monotone operator learning with Lipschitz regularization, it's stabilized to something like 0.95 or something. Again, that's a parameter. So if you go back, you can control this beta to enforce that constraint more strongly or less strongly. So by choosing beta, we can make it closer to 1 or no. So this was the Lipschitz constant, and you can see that the number of iterations you need for the algorithm to converge to a fixed point depends on the Lipschitz constant. So if the Lipschitz constant is small, for example, in the spectral normalized one, you need very few iterations. It converges pretty rapidly. So the green one is the model approach with 2 unrolling steps, and this is the one with 10 unrolling steps. Now, the Lipschitz regularized one converges in about 35 iterations. And if you don't apply any restrictions on the Lipschitz constraint, it just blows up. Okay, you can see that it quickly diverges. Now, in terms of the training error, we see that the model with 10 iterations gave a lower training error. So this probably talks about, touches upon what Sai was pointing out. If you don't have this constraint, you can get a better performance. So you take a small hit in performance, but the benefit is that you have robustness, and also you can work with significantly lower memory. So the memory requirement for this blue one is about 10 times smaller than what you need for this magenta one. And here are some results. I mean, again, this is work in progress. This is a conventional sense, and this is the monotone operator learning setting with spectral normalization. This is the model with 10 iterations, and this is the proposed approach. So you see that you get performance somewhat comparable to model. There's a slight decrease in PSNR, but the benefit is that this reduces the memory requirement by about 10-fold. So the benefit is significantly reduced memory, guaranteed convergence to fixed point, uniqueness and robustness to perturbation, and Lipschitz regularization. So that's all what I wanted to talk about MOL, the monotone operator learning. I can pause to take any questions if you have any questions. If not, I mean, just let me know. I can, pause anytime. So one of the problems with traditional model-based deep learning is the high memory demand. Another problem I mentioned is the lack of training data. So we'll just talk about some of our approaches to mitigate this problem before we move on to the extreme large setting. So ground truth is often not available. So the question is, can we learn from undersampled data? So the problem is that we have undersampled data and also undersampled data challenged by noise. So so basically one approach that had been used in the literature is the Stein's unbiased risk estimator. So this was originally introduced to deal with denoising. So there are several people who have introduced Sure for training deep denoisers. So the problem setting is as follows. So B is equal to rho plus N. So rho is the unknown image and B is the measurement. Now we don't know the noise-free image. This means that we cannot calculate the mean square error. So the Stein's unbiased risk estimate allows us to approximate this mean square error by computing something like this. Okay, so here we are not using rho, we are only using the measurements B, which are noisy. And to correct for it, we are adding an additional term as shown here. And the good thing is that this Sure estimate is an unbiased estimate of the mean square error. So if you had a lot of data, this will closely approximate the mean square error. So this was used in a variety of settings for finding the optimal regularization parameter for iterative algorithms and also for training deep denoisers. So this approach was also generalized for undersampled measurements by Eldar in 2008. So they introduced something called as the projected MSE. So let's say now we have an undersampling operator A. In this case, it's impossible to look at the true MSE, but we can look at is the projected MSE onto the range space of AFS. So this is what I call as PMSE. And they came up with G-Sure, which is a generalization of the standard Sure, which is an unbiased estimate for the projected MSE. So one of the challenges is that this projected MSE is a poor approximation for the mean square error because you have a projection step here. So this means that you're only looking part of the data and not the entire data. So in this work, Metzler looked at training deep, unrolled networks using this G-Sure approach, and they found that this approach was not very competitive. So at the end, they just did a layer by layer training. So they took each layer and trained denoisers, assuming Gaussian noise, and which was regularized using Sure. So our approach is really simple. So we just use different undersampling patterns for different images. So in the MRI setting, this is really easy. So you can undersample every image, but undersample every image in a different way. And let's say your goal is deblurring, from natural or camera images. You can assume that the blurring that's present in each image is slightly different. So if you take the ensemble of them, you get the ensemble MSE, which is as shown here. Now, in the MRI setting, you have variable density mask, which means that you're oversampling the center of K-space. So this means that when you're doing the ensemble approach, you're giving more weight to the center of K-space and less weight to the outer K-space. You can look at an ensemble weighted MSE to correct for it, somewhat like the density compensation used in non-Cartesian MRI. So you can apply a density correction here and then look at the ensemble weighted MSE. So the N-Sure approach that we introduced is basically based on this data term, which looks at this term here, the ensemble weighted MSE as a data term, and then you have a divergence term very similar to the standard Sure scheme. So how do we compute it? So you have two terms. This is the data term, and this is the divergence term. So the data term is doing a reconstruction of the images using an unrolled network or UNet or whatever you like. And rather than comparing it to the ground truth, you compare it to the least square reconstruction. For example, in MRI, it's a sense reconstruction. So you don't compare it to the ground truth images, you compare it to the sense reconstruction. Now, to correct for the fact that you're not comparing to the ground truth, you have the divergence term, and this is computed using the Monte Carlo Sure approach. So you basically add a perturbation to the input and measure the difference, and that's how you get the divergence term. So how does this work? So this is some comparison, on a data set, an MRI data set. So if you use the supervised MSE, you get a pretty good reconstruction. Now, if you use the LDAMP approach, which is a layer by layer training, you take a hit in performance. Another approach is you just look at the k-space mean square error. So you just have few measurements. Why don't we just use the error there? So there also you take a slight hit in performance. SSDU is one of the recent unsupervised methods, and Ensure is the proposed approach. So you see that with Ensure, you get pretty close to the supervised MSE, even though we don't have ground truth available for training. And again, this was introduced to deal with noise. So what happens when you add a lot of noise? Even there, we find that the Ensure approach gives somewhat similar performance as the supervised MSE approach. So this is one of the approaches that we've used to deal with the fact that we don't have fully sampled training data. Again, this is another active area of research that a lot of you are contributing. So that's a really exciting field to be in. Now, this approach can be used for a variety of settings. For example, deep image prior that is used for single shot learning. It basically tries to take the output of a generator and compare to the measured data by using a loss as shown here. And it's using the fact that neural network can learn natural images faster than noise. So one of the problems here is early stopping. So you need to stop the algorithm sooner, otherwise it'll start learning noise. So you can mitigate the same thing. You can stabilize it using a sure loss. So if you use a standard MSE, you'll see a degradation in performance with epochs. Whereas if you use a sure loss, you get stabilization. So you can see that by using sure, it doesn't matter where you use UNet or model, you get stable results with a higher PSNR if you use this approach. Okay, it's again showing the same kind of results. And you can also use this for model adaptation. So let's say you train one model, let's say in one center, and you want to translate it to another center. You don't have to train all over from scratch. You can do model adaptation using this sure framework with a few data sets. Okay, so finally, I want to go to the large scale setting. So we saw that the deep equilibrium models can help. It can reduce the memory requirement by a factor of 10, but that's often not enough. Okay, so when you're dealing with these large scale approaches where you have to reconstruct large volumes of data over time, none of these approaches are going to work because let's say with DQ, you can increase the number of slices from 1 to 10. But here we are talking about reconstructing volumes over time. So it's impossible to use an unrolled approach for this setting. So we were looking for an alternative, and we were inspired by this deep image prior approach. So basically, the property that we are exploiting is the same. So we are assuming that all these images lie on a smooth manifold in high dimensional space. So how do we deal with data that's lying on a nonlinear manifold? I mean, there are multiple methods. You can learn dictionaries that does a union of subspace. A simpler approach would be to do a nonlinear transformation. Okay, for example, if you do a nonlinear transformation, which is x squared and y squared, you see that points lying on a circle will now lie on a line. And now you can fit a subspace here, which is equivalent to fitting a circle onto the real data. So you can do it in two different ways. One is that you apply a nonlinear transform and fit a straight line here, or you can fit a straight line here and then take a nonlinear transformation to generate the data. So we follow the second approach. So we assume that the images in the time series, so let's say you have a time series of images. So we assume that the images in the time series are generated by a CNN generator, which is basically implementing this nonlinear map. Okay, so our data is lying on a subspace, and we are taking a nonlinear transformation to create the images. So we are implementing that nonlinear transformation by using a neural network. So we're basically learning this latent space as well as the generator. So this is just an alternative. So I talked about these two approaches. One is like you start with the latent space and apply a generator to get the image manifold. There's an alternative approach, which is you work in the image manifold and you apply a nonlinear lifting to the latent space, which was related to some of our earlier methods. So you find that this method is significantly more powerful because it uses the power of CNN generators. So what is the idea? So we consider a neural network, and we assume that we have some latent variables. So the latent vectors are shown like this. So we have a free breathing and ungated cardiac MRI. So there is both respiratory motion and cardiac motion. So you're learning the latent parameters, and these latent parameters are going to capture some of the properties of the images. Okay, for instance, they're going to capture the respiratory motion, which is shown in blue, and the cardiac motion, which is shown in red. So these are CIs. So these are fed to a generator, and the generator generates all these images. So how do we learn these generator parameters? So we are simultaneously learning the generator parameters and the ZIs in a deep image prior like fashion. So we're trying to minimize this loss such that the loss is basically you take the Fourier transform on each of those images and compare to the measured data. So there are a couple of things that you have to keep in mind. So basically, we are doing a lifting from a low dimensional latent space to a high dimensional image space. So we want to come up with some isometry. So in other words, the distance here should roughly match the geodesic distance on the manifold. So there is a relationship between these two distances, which is related to the Jacobian of this mapping. So if the Jacobian is very high, or you get a very high Jacobian norm, these two spaces do not have any correspondence, which is bad. So we add a regularization term to enforce an isometry between this low dimensional latent space and the high dimensional image space. And we also add, so we know that the images do not change rapidly in time. So we also add a latent regularization to enforce it. So here's where we are studying the impact of the regularization terms. So we see that if you don't use any regularization, you get really meaningless latent vectors. Whereas when we add the regularization, we get meaningful latent vectors that capture the cardiac and respiratory motion in the cardiac setting. So here are some results. So this is our earlier approach, which uses the alternate approach of working in the image space and projecting the lower dimensional subspaces. So this works well, but it requires about 40 seconds from per slice. With the proposed approach, which is using the deep generative model, we can reduce the scan time by a factor of 4. So we can work with roughly 12 seconds per slice and get somewhat similar image quality as what Storm is able to give at 40 seconds per slice. And we also compared it against the standard Storm method with 12 seconds. So you can see that it results in a lot of noise amplification. And again, some of these competing methods are not giving excellent results. So these are some examples. So we tried this on a COPD subject who is at risk for pulmonary hypertension. So the algorithm is able to resolve the cardiac phases and the respiratory phases well, while giving pretty good reconstructions. So now we also wanted to generalize this to multi-slice imaging. So usually cardiac MRI is collected slice by slice. So you collect one slice followed by the second slice and so on. So the subject is breathing freely and also his heart is beating while the data is being acquired. So the current approaches just treat the reconstruction of each slice independently, and there might be different breathing patterns and heart rate. So one of the problems with these current approaches, and including the approach that I just described, is that it cannot exploit inter-slice redundancy. It cannot exploit the redundancies between the slices. And post-reconstruction, we need to align the slices to get a good reconstruction of the volume. So this can also be accounted by using a multi-slice generator. So you create a 3D generator. So rather than generating one slice, it now generates a volume. And you can have different latent vectors to capture the variability in each of the acquisition of each of the slices. So the goal here is to jointly learn a 3D generative model, and each slice will have its own latent vectors that capture the cardiac and respiratory motion. And after reconstruction, we just excite the latent vectors, excite the generator with the latent vectors of any particular slice, and it'll generate a synced volume. Now, if you directly apply it, and if you excite the generator with, do the learning, and you excite the generator with one of the latent vectors of one of the slices, you get these reconstructions. So here we are exciting with the latent vectors from one of the second slice. You see that you get pretty good reconstruction close to that slice, but as you move away, you start to get some distortions. And the reason is that the latent vectors will have very different distributions. So we have a variational formulation, which also imposes a prior on these latent vectors. So we constrain these latent vectors to lie in to have a Gaussian distribution. So with that, we get pretty good alignment. So you can see that unlike this scheme where each of the latent vectors will have totally different distributions, we have roughly the same distribution there, and that significantly improved the image quality. So especially if you look at these slices, you see that you get better image quality here. And hopefully you can see this from here. So you get pretty good image quality on all slices. And more importantly, all of them are aligned. So this is just a movie illustrating how the reconstructions look like. So each of these slices are collected from different acquisitions that might vary in cardiac and respiratory motions, but the reconstruction kind of combined all of them and gives you a synced movie. So one of our collaborators, Sajan, he's really interested in speechMRI. So in speechMRI, you need to have high dynamic rate. So typically you collect one image at a time. And usually they speak something, for example, in this case, they are saying sana, sa, luli, lala. And you repeat that for each slice, okay? And you can reconstruct each of the slices independently, but then this occurrence might happen at different time points. Now, using this approach, we can jointly reconstruct all the slices, and then everything will be aligned, and that also improves the image quality. So here, unlike the previous setting, we use a lot of latent vectors. So we had to use about 10 latent vectors here to get pretty good reconstruction. So here's just an illustration. So each of the slices are collected separately, but by jointly exciting the generator by using the latent vectors, you can see that all of them are synced and the image quality is really good. And so Sai, how much time do I have? Am I running out of time?
Yeah, I think we are hitting the hour. So yeah, maybe I think you can wrap up and we can do more questions in the end.
Okay. Yeah, so finally, I just wanted to mention that this can be also extended for motion compensated image recovery. So the idea is that we're not trying to learn images here. We'll try to learn motion fields by using the same approach. Now we can deform a template image using these motion fields and match to the data. So using this, we can really scale up. So we can look at 256 by 256 by 256 by 1000 volumes. So this is a lot of data, but this generative model can run in about half an hour to do the reconstructions. So you can see that it gives pretty high resolution reconstruction of the human lung. And more importantly, it's also robust to bulk motion. So for example, if you focus here, you can see that the subject just moved his hand. So the conventional methods are not able to reconstruct the image volumes this way. So this approach can detect these bulk motions and also correct for it. And it gives pretty good reconstructions compared to the traditional methods. And right now we are working on generalizing this to pediatric imaging. So this is a 24-month-old baby that was imaged. So using a specialized MRI hardware, and it's a really small scanner, but just has a body coil, so the SNR is not that great. But you can see that the baby is kind of moving in a crazy fashion. Nevertheless, the algorithm is able to do a pretty decent reconstruction, which can be seen from here. So many of the competing methods kind of fail in this case, whereas this algorithm still is competitive. So we're still continuing to work on it. So finally, I'd like to wrap up. So basically, we wanted to take some of these model-based deep learning algorithms that had been used in the small scale setting, and we wanted to scale up. We see that deep equilibrium models is one of the approaches. I mean, it can significantly reduce the memory by a factor of 10, but it had some problems such as uniqueness and so on. So we generalized this using the monotone operator learning framework, which offered several nice properties such as stability without compromising too much on image quality. Now, we can also deal with the fact of not having fully sampled data by using unsupervised learning, by using SURE. And finally, this GStorm method or the generative storm method allows us to scale it up to a level where we can apply it to volumetric data. So I'll stop there. And finally, I want to thank all the people who did the hard work. So this is my group, my current collaborators, as well as the past collaborators, and also the funding sources. And just another plug, I mean, so we're looking for people. So if any one of you are interested in the work that I presented, please contact me if you're interested. So I'll stop there. Thank you for your attention. And sorry, I ran over time.
Thanks, Mathews. Thank you. I think that was lots of interesting work in there. Great to hear.
Thank you.
I think maybe I can start with some questions, and then folks in the audience, if you have questions, just post it in the Q&A, and we can have Mathews answer. I was wondering, so with the DIP approach, did you have to play around with the network architecture and other parameters to get it to work? Like, what were some of the engineering challenges when in that framework?
So you're talking about the dynamic data sets, or yeah. I mean, I think one of the problems is that it's a stochastic gradient descent kind of an approach, and you cannot deal with all the data at once. So you use a pretty small batch size of one image per iteration, and that results in a very slow convergence. So one of the steps was, we had an alternating approach. So basically, how do I explain this? So basically, we simultaneously solve for theta, which are the parameters of the generator, and the latent vectors. Okay, let me just go back to the corresponding slide so that I can. Okay, over here. All right, so we are simultaneously solving for z and theta, but just to speed up the convergence, we just use an alternating strategy where we freeze c and then solve only for theta, which allows us to go much faster. I mean, basically, we can take the latent space, bin it into a few different states, and solve for the generator parameters. So we had to do that, and that significantly improved the performance. So previously, the runtimes were like hours, but using the strategy, we were able to reduce it to 20-25 minutes.
Mm-hmm. And I like the DIP framework in the case of dynamic data, because you assume if you're doing this frame by frame, then you have a lot more BIs to sort of adapt the network over versus the conventional DIP, which is like just one image, and then right. So that if you overtrain it, you obviously overfit the noise. Right. Whereas here, having some diversity in sort of among the slices may be helpful. Did you ever try? I think you talked about the multi-slice thing. So here, does it work if you try to learn, like if you just had one cardiac sequence and you try to learn the network like in 3D on the entire sequence, versus doing it slice by frame by frame, slice by slice?
Can you repeat your question? So you are saying, what if you had a 3D network and learn it only from one slice? Is that what your question is?
No. If what I'm saying is, if you had a cardiac sequence and only the k-space measurements, how would sort of learning the network parameters theta, but sort of doing it, the network is for each frame, versus that would be like a two-dimensional network versus having a three-dimensional network on the entire thing. So
so there is significant improvement in performance. I can, okay, maybe this is more evident in the speech case. So this is a 3D network that we're learning. And here, I mean, again, it's not an apples to apples comparison. I mean, this is with a earlier version of our algorithm, but it's solving it slice by slice. So you can see that here, you're still keeping some of the residual aliasing and so on, whereas it's all cleaned up here just because of the diversity in the sampling patterns, and also the fact that you're learning a 3D network as opposed to a 2D approach.
Right. So, so what is the challenge? Because then if you're doing it in the DIP way, you have significantly more parameters if you just move from a 2D network to a 3D network on the same data. So would you have to be more careful about early stopping and other engineering tricks?
Well, okay. So you're saying, okay. So first of all, this is a completely unsupervised learning approach. So we have to learn a different network in the 2D case for each single slice. Okay. So we're not saving. So we're not trying to learn a single 2D network over all slices. For each slice, it's a different network that we're learning. So, so the computational complexity there is a little higher. And again, there's no significant benefit in in jointly reconstructing all of that using a single network. In the 3D case, we are jointly reconstructing everything using a single 3D network. So it can combine the information across slices and also across different acquisition schemes.
Okay, that clarifies. I think that, that makes sense. Yeah, I was mentioning sort of having a common network across the frames or slices as a means of then you're sort of in the regime where you have more sort of training data for fitting those parameters of that network. But yeah, I guess I agree with you. It may not give you the richness in the model to match performance compared to having it vary across slices or doing it fully 3D.
Yeah, I totally agree with you. Right now we are not, benefiting from pre-training. This is so the computational complexity is about 20 minutes for this 3D network. If we were able to pre-train it somehow, that could significantly improve the performance and also reduce the runtime. We're still working on ways to getting there. We're not there yet, but you're completely right. There might be some value in learning something that's common across slices, as opposed to learning an independent network for each 2D slice, but you're not there yet. Yeah, that's a great idea.
Cool. I had one last question, which is the latent code Z. So did you see that when you optimized it together with the network versus letting it be random? Did you see that the optimization was indeed, a good thing?
Yeah, so basically that is, you're talking about this time DIP approach from Michael Unser's group. So that's the time DIP approach. So they just chose the Z vectors to be random. Well, not completely random. They just fixed it as a random code every several time points and interpolated in between. And then it was fed into a DIP scheme. So that gave these results, which are a little bit worse than the results we get. So we find, and again, our approach is a little bit more interpretable because these latent codes are capturing some of the variability in the data, like cardiac motion and respiratory motion. So as you might see from here, you can see, now you can go over the different latent codes and see how. So actually what we do is we freeze it. If you want to see a diastole phase, you can just stop there, as opposed to here. So you can switch from systole to diastole by simply moving over the latent space. So that's a huge benefit with learning some meaningful latent codes as opposed to randomly choosing it.
Mm-hmm. Yeah, I think that I totally agree. This is, I think, quite interesting. All right, so thanks, Mathews. I think we don't seem to have other questions. Yeah. In that case, yeah, maybe I can hold a couple seconds. Anyone in the audience, feel free to chime in. Okay, so if not, let's thank Mathews for his wonderful talk. And it was great having you, Mathews, in our Space West webinar series. And also for the audience, this will be the last webinar for the Space West part of the series, but I believe Space East may have one more. So do feel free to check our website, or if you're one of the registered participants, you'll get an email notification on that from them, from Space East. And then I think we'll start up again next year. So that information, the next season information should come up on the website once it's finalized. And so that's still in the works, but we hope to see you next year, hopefully. And hope everyone has a good end of the year, and happy Christmas, Happy New Year, and everything from the Space West organizers. Thank you. Bye.
Nice.